Okay, now we have to determine the pressure of the hydrogen gas that is in the eudiometer. The lab, such as this technique we did, it is said to, it's called collecting a gas over water, which basically means that we bubble the gas through water. Now, when you bubble the gas through water, the sample in the eudiometer contains both the gas, in this case hydrogen, and it's also going to contain water vapor. So in the eudiometer, this picture here represents a eudiometer. After reaction is complete, we have hydrogen gas in the eudiometer and we also have water vapor. So after the reaction was complete, when I did this lab, I allowed the pressure of the hydrogen and water in the eudiometer to equalize with the atmospheric pressure. So picture the beaker, if you will, that was in the lab. The atmosphere is pushing down on the water in that beaker. And initially, it was pushing water all the way up to the top. As the reaction proceeded, hydrogen gas was produced and the meniscus moved down the eudiometer towards the water. So when I allow the two pressures to equalize, that means the pressure of the hydrogen gas and the water vapor inside the eudiometer is equal to the pressure of the atmosphere, which for this lab was measured to be 30.02 inches. So we are studying the ideal gas law, and we want to work with hydrogen. Since you already know the moles of hydrogen you calculated previously in the lab, we need to know what the pressure of that hydrogen is. So how can we determine the pressure of just the hydrogen? Well, we're going to apply a new concept, which is called Dalton's law of partial pressure. It's not a terribly complicated law. It basically states that the total pressure of a mixture of non-reacting gases, in this case, we have water vapor and hydrogen, the sum of the partial pressures of the individual gases is equal to the total pressure. So basically, all it's telling us is the total pressure of the gas in the eudiometer is equal to the pressure of, in this case, we could have P1 be hydrogen and P2 would be water vapor. So at equilibrium, the pressure of the hydrogen plus the pressure of the water must equal the barometric or atmospheric pressure. Let's go back up top here and just think about this again. So what we are saying is that in that eudiometer, the pressure of the hydrogen, the pressure of the water vapor together must equal the pressure of the atmosphere or barometric pressure because they're at the same height. So to figure out the pressure of just the hydrogen would stand to reason if the total pressure of hydrogen plus water vapor equals atmospheric, then the pressure of the hydrogen would simply be the atmospheric pressure minus the pressure of the water. So once again, developing the equation at equilibrium, atmospheric pressure, also called barometric pressure, and the pressure of the hydrogen and water added together are equal. So rearranging this equation, I can calculate the pressure of the hydrogen by simply subtracting the water vapor pressure from the barometric pressure. So when you go back to work on the lab, you're going to need to convert the barometric pressure, which is 30.09 inches, you need to convert that to kilopascals. And you're then going to look up the vapor pressure of water at the temperature which the lab was conducted, subtract that from the barometric pressure, and you'll have the pressure of the hydrogen. That will be the value that we're going to have to use in the equation PV equals nRT when we solve for R.